This video is going to be an introduction to chemical equilibrium. We're going to use this reaction as an example. 3 moles of hydrogen react with 1 mole of nitrogen to form 2 moles of ammonia. So if we start with all reactants, then this reaction will proceed in the forward direction toward products to the right. And we're going to, each time we lose 3 molecules of hydrogen and 1 molecule of nitrogen, we form 2 moles of ammonia. Eventually what happens is we begin to accumulate a lot of product on the right-hand side. And as we learned in the last chapter on kinetics, when we get lots and lots of that compound on the right-hand side, then they're going to start to collide with each other. And then what happens is the reaction becomes more significant, and it begins to occur at a significant rate. And that's because we've accumulated a lot of ammonia molecules. And so 2 ammonia molecules will collide, and they will move to the left and produce the reactant molecules again. So we'll start to, and the reverse reaction will become equal. When they become equal, that is a state called equilibrium. So when the forward reaction rate equals the reverse reaction rate, then there is no net change in any of the reaction component concentrations. The concentration of hydrogen and nitrogen and ammonia will remain constant. That state is called equilibrium, and we use that new arrow like you see there. We're going to talk about the arrow in a minute. So this is a graph from your book that shows concentration as a function of time. Each of the 3 reaction components are shown. So you can see that hydrogen, which is green in the graph, and nitrogen, which is blue, those are both reactants in this particular reaction, and they decrease in concentration over time. And then the ammonia increases in concentration over time. That dashed line you see there, it shows when equilibrium is achieved. Chapter 12, the last chapter we covered on kinetics, really dealt with the left side of that graph. We looked at similar graphs. But now that we're in chapter 13, we're going to talk about the right-hand side of that graph, once all of them remain constant over time. This image is meant to show you, this left graph is the same one I just showed you, but the one on the right is basically, instead of starting with hydrogen and nitrogen as reactants, we start with just ammonia as a reactant, the orange one, and that one decreases in concentration over time, while hydrogen and nitrogen increase in concentration over time. So basically the graph on the right shows you the reverse reaction, and this is just meant to show you that equilibrium can be achieved from either direction. So from our little cartoon, if we start with 100% product, then those product molecules are going to collide with each other, and they are going to produce hydrogen. And then hydrogen will begin to accumulate, and eventually they will accumulate in the reverse. And eventually they will also come to equilibrium. And it is still achieved starting only with everything on the product side. So the first thing I want to mention about chemical equilibrium is that equilibrium is dynamic. So reactants get converted into products, and even though the concentrations are constant over time, it doesn't mean that nothing is changing. It doesn't mean that nothing's happening. So the first really important point is that equilibrium is not a static state, it is a dynamic state. And so what we said is that at equilibrium, once equilibrium is achieved, the concentrations of all of our reaction components, in this example, hydrogen, nitrogen, and ammonia, the concentrations are going to stay the same. And so if you just, put on your molecule glasses and check in on the reaction, once it's reached equilibrium, if you add up the number of hydrogen atom molecules, the number of nitrogen molecules, the number of ammonia molecules, they're always going to stay the same. And it makes it seem like nothing's happening, even though that's not actually true. So the first point is that equilibrium is a dynamic state. So if we think about what's happening here, if we imagine, okay, these 3 hydrogen molecules are going to combine with this nitrogen molecule, and they're going to form 2 ammonia molecules on the other side. At the same time, however, 2 other ammonia molecules, maybe the same ones, maybe different ones, I'm going to pick different ones, they're going to react decompose to form 3 molecules of hydrogen and 2 molecules of nitrogen. And so even though it appears that nothing's happening, you can see that we constantly have the forward rate moving, we constantly have the reverse reaction moving, and it just so happens that because the rates are equal, the concentrations remain constant over time. So the best example is your bank account. So if you think about your bank account, right, you have a paycheck that goes in once a month or twice a month or however often you get paid. That goes into your bank account. And then think about all the things that come out of your bank account on a regular basis. You pay rent, you gotta live somewhere, and then you're paying off your car a little tiny bit at a time, and then other things. Everybody's got to eat, so you got to get groceries. And then there's always the inevitable stuff that you've got to get at the mall, right? All those things go out, right? So the paycheck goes in, but all these other things go out. And so your bank account is a constantly moving stream of money, right? The paycheck goes in, everything else goes out. The paycheck goes in, everything else goes out. The paycheck goes in, and the money goes around and around and around and around and around. And even though money's constantly flowing, it always seems like you only have $2 in your bank account, right? So there's constant flow, but there is the same constant sad balance that you always seem to have. So point number 1 is the equilibrium is a dynamic state. Point number 2 is that equilibrium is represented by a new type of reaction arrow where the arrow goes in both directions. There are 2 separate arrows, and we often have it where it's only got one arrowhead, as you see there. So it's important that you use the right kind of arrow because other kinds of arrows mean different things, right? You learned about resonance structures in Chem 101. That is a different arrow than this arrow. So it's important that you recognize that this corresponds to equilibrium. The third point is that there is an equilibrium constant, which is represented by a capital K, as opposed to the lowercase k, which we've been using for the rate constant. And so the next thing we're going to talk about is the equilibrium constant. So we're going to talk about how you write equilibrium constant expressions, and we're going to start with the general reaction equation and how you would write the equilibrium constant, and then we'll do some practice. So for our general reaction equation that we see here, where we have lowercase letters representing stoichiometric coefficients and uppercase letters representing reaction components, A and B are reactants and C and D are products. So these lowercase letters, A, B, C, and D, that I'm underlining in green, remember those are the stoichiometric coefficients, so those are going to be numbers. And then the uppercase letters are going to be compounds or molecules or elements, whatever the reactants and products actually are. If this is our generic equation and we write the expression for capital K, the equilibrium constant, then you see it here. We have the concentration of C raised to the C power times the concentration of D raised to the D power. So the products always go in the numerator, and then the reactants go in the denominator, concentration of A to the A power, concentration of B to the B power. Now remember that these are multiplied, not divided, and remember that the brackets mean molarity. And then the other important part of this is that these concentrations, the molarities you see, those are the concentrations at equilibrium.